Hi, my name is Jim, and today's topic is fiber optics. And we start with dealing with photons, which are the underlying energy that has to do with fiber optic transmission. And what is a photon? Basically, it's a wave and a particle. It's both at the same time. It's very confusing how you can have a particle and a wave, but same is true of electrons. They are waves and particles. And the energy of a photon is E equals h times F, where h is Planck's constant, which is discussed in the homework. And F is the frequency. So photons have specific frequencies. And for example, a blue light photon has more energy than a red photon, has more energy than an infrared photon, has more energy than a high-frequency radio wave, has more energy than any radio wave. So at lower frequencies we talk about electromagnetic communications in the terms of radio waves, and at light we talk about it in terms of photons or waves. But basically it's a continuation of a spectrum that goes up and through ultraviolet, X-rays, and cosmic rays. So the energy is kind of important here, and when it gets into fiber optics, what we want to do is choose the frequency of our emitter, which can be either a LED or a laser, such that it takes advantage of the fiber's lowest loss points, because fiber is not flat, if you will, across the frequency spectrum involving light. It has a particular dip, and that's where we want to be. So sources for fiber optic systems, FO hereafter meaning fiber optic, are LEDs and lasers, and the detectors are photodiodes, and there's a special type called a PIN diode, and what that stands for is it's P-type silicon with an intrinsic layer, which basically is a very, very lightly doped layer, followed by N-type. And what that effectively does is it increases the area in which a photon impinging upon the diode can generate an electron-hole pair. So compared to a regular glass diode, they're much more efficient for generating current. And we also have another type called an avalanche photodiode, an APD, and it's kind of similar to a PIN, except it operates very near the breakdown potential of the diode. So if a photon generates an electron-hole pair, as the electron speeds past other electrons, which are in a non-excited state, it imparts energy to them, and then they break down and in turn pass other electrons and so forth. So one photon produces an avalanche of electrons, and the latest reading that I've done on it is it's possible to get 80 to 100 electrons per photon. Now you can kind of see by the range of that an APD is noisier. Don't know how many electrons it's going to generate. It's more sensitive, and the circuitry is more expensive because it's you have to operate near the breakdown region, certainly not in the breakdown region. So those are the two types of detectors. And these fiber optic systems are used nearly exclusively for digital transmission, and the exception of that would be backbone cable TV. Now that means that if you have a head end and you want to get out to a distant neighborhood, you could modulate all of these carriers, which some may be analog, onto a very, very linear laser and get that signal out to a distant neighborhood, then break it down and do the feed after that in coax. So what is a fiber optic? And actually it's a piece of plastic. We call it glass, but it isn't. It's flexible, and it has two components, a core and a cladding. And this is kind of an example of that. Core is in the center and the cladding surrounds it, and you cannot see the difference here. The the core is doped, that is, has impurities in it, such that its refractive index is 1.5. So the core velocity of propagation for light is less than that for the cladding. It may seem counterintuitive, but that's the whole reason that fiber optics works, is light goes faster through the cladding than it does the core. So this is done at manufacture, and if you look at the end of one with a microscope, you cannot tell where the core ends and the cladding begins. So what we have here, and the reason this works, is something called diffraction, and that's bending of light or radio waves. Now, radio waves can be diffracted by striking the ionosphere, and all that means is that they're bent, come back to Earth, and that's sometimes called skip. In fiber optics, they're bent because, I have a diagram coming up here of if you view this as a planar wave, it'll actually speed up when it hits the interface and be refracted back into the fiber. So what this is called is total internal reflection, TIR, and it's what sits under the hood of why fiber optic systems work. So we have the N here, the index of refraction, and that's simply C divided by the velocity of propagation through anything, really. Water, for example, has an N value of 1.33. Now, N has to be greater than 1 because C is equal to 1. Now, in air, the speed of light actually slows down a very, very, very small amount. But we overlook that and just say that it's equal to 1 for a value of N for air. So let's see, light travels faster through the cladding. That's very core to understand how this works. Now the cladding in turn, and this is just a piece of very, very thin plastic, and a lot of people are injured by looking at this and not seeing the end of it, and it actually sticks them in the eye. So you have to be careful if you're looking at a piece of fiber which has the protective plastic sheath which sits around the cladding removed. So you're just not going to be looking at a piece of fiber. It's going to have some kind of external protection on it. You don't want to nick it, you don't want to scratch it, and things like that. So, if you like to buy a fiber optic cable, other than a jumper, which would be connector rather, which would look like this, it would come in a what's called a 6-pack, and it typically has some kind of armor on the center of it, and that's just to give it strength, because with plastic, if you pull it, it'll stretch, of course. So if we have a way to identify this, or a way to identify this, is each strand is wrapped in a different color thread. So imagine that you're out on a construction crew and there's been a dig up or a steam pipe break in the street. They typically leave extra in manholes. So you go to the nearest manhole, pull out enough of this, and then you'd be using the identification to splice these so that the same fiber that was broken gets connected to the right fiber for continuity. Further, cables come in multiple 6-packs, and to identify those, each 6-pack is wrapped in color thread too. So you have a way of identifying every single thing in a relatively large fiber optic cable. And a slang word for that is backhoe fade. That's when you dig up something and take out the fiber optic cable. As far as getting across the country is concerned, railroad right-of-ways, pipeline right-of-ways, things like that are the way that the fiber is laid, that being considerably better than stringing it on a pole. Okay, let's see, we have two general types of fibers. And these are systems, I shouldn't say fibers. And one is a multimode, and it's a relatively large core, up to 125 micrometers. And it supports multiple modes, which means the different reflection of light rays. So a light ray is a word typically used in fiber optics to explain what we're seeing inside of it. They are particles and waves, but ray works well for a good visual on this. So you can have multiple rays here. You can see these bouncing around. All of these here are subject to total internal reflection, and what our hope is they end up coming out of the other end of the cable. Now, the color of multi-mode, especially, and this is the part that you'll typically be seeing, is orange, because we need an easy identifier for this, because, well, once we have it, you're not going to be able to tell by looking at the core whether it's single mode or multi-mode. But a little bit more on that later. So it can be used with a light emitting diode, and that's kind of a good thing, because LEDs are significantly cheaper than lasers. Now, this here is an optic trainer I was starting to build, and this here is a fiber optic LED. Its launch power is negative 12 dBm to negative 16 dBm. This is the receiver. These cost about $21 a piece, and they're designed using a commercial grade ST connector. Now, there's a whole bunch of different connectors. The one thing you have to be very, very careful about when handling one of these is you don't get your fingerprints on the end of that. Because a fingerprint at these wavelengths is a mountain. It causes all kind of issues. Namely, it reduces the received power level. There are kits available to clean these, and you have to be very careful with them. Now, cleaning out the inside of this is done with compressed air, wearing safety glasses, of course. So this kind of attaches like a BNC connector. You have to rotate it to pick up the slot, or not. There we go. Then once you get that, you push it in and twist it, and then it locks in place. It's spring loaded, so that this is held as close to the light emitting diode or the photodetector as possible. Multi-mode have limited distance, and where they're very good is in a enterprise corporation, is for the backbone of a network. The wavelength, and in fiber optics we speak of wavelength, not frequency, and this is not an OT, angstrom units. This is nanometers, and for multi-mode that typically sits around 850 nanometers. Now, what does that really mean? Well, visible light ends in red about 750, so this is a little bit beyond red into infrared. Now, everybody's familiar with infrared, sort of, in that that's what your remote control from your television set uses, is infrared. Now, on the other hand, we have single mode fibers, and this is where the core is very narrow, and it only supports one mode. That is, a ray travels down the center of it, and it is also following the total internal reflection. I haven't shown any in here because it's so small. So single mode fibers are good for long distance, because we don't have the issue of pulsed spreading, which we'll see in a minute here. Now, let me back up to this for a minute. As you see, this particular ray is going to have a longer distance than this ray. Now, what that means is that if we have a pulse, this is going to arrive sooner than this one, and that produces pulse spreading. And what pulse spreading leads into is intersymbol interference, plus it reduces the amplitude of the pulse. It's spread out. In single mode, we don't have that. It's used with lasers. It has to be very carefully coupled. And the frequency of this sits around 1300 to 1550 nanometers. So it's lower in frequency than multi-mode. It's good for long distance, and of course it costs more, which is the reason why multimode is used in establishments where you do not need the distance. If you're going cross-country, the optical signal, and there's loss in fiber cable, of course, is not amplified. The receiver gets it, and it's called a repeater. It knows what the signal should look like, so all it does is determine the ones and zeros, if you will, and then reconstructs them. It doesn't amplify them. It generates a brand new pulse and ships it on the way. So the only thing it would be subject to would be errors, and that would be where a 1 and a 0 bit are complemented. And that's up to the physical layer and the above layers to take care of that through ignoring it or requesting packet retransmissions or incorporation of forward error control. But that's at a level much higher than this here. Yeah, this is called the physical layer. And single mode jumper cables are not orange, they're either yellow or black. So it has to be very clear what the jumper's for, because if you get the wrong one in the right place, what's going to happen is a loss. And there's absolutely no question about that. Let's talk about losses in a fiber. Of course, we know transmission lines have losses, and basically a fiber is a transmission line. It guides energy, just like coax cable would, and one of the losses is referred to as Rayleigh scattering, and this is caused by relative difference in the densities of the cable when it's made. So that would be the density of, say, the core material, and what that does is it causes some refraction, and the ray may be lost if it impacts the core cladding at the wrong angle. So a process improvement reduces this type of loss. Next we have absorption, and the first listed is ultraviolet, and it's not really important because we do not operate anywhere near the ultraviolet range, but fiber cables absorb this. Also, and this is kind of bad, is we have infrared absorption, and some of the photons end up being absorbed by the core material, and that energy is converted into heat, so they don't come out of the other end of the cable as a useful component of the signal. We also have OH ions, which basically are remnants of water, and they have places where they will absorb infrared. So when we decide what wavelength we're going to operate on, we have to stay away from the absorption peaks of the OH negative ions. We have leakage, and this is through the core and cladding interface. So the total internal reflection is not 100% always effective. And then we also have something called mode coupling losses. Now, this can be imperfections of the core and cladding interface. Perhaps it's not consistent. Variations in the core diameter. So if the core changes diameter, essentially what that'll do is in places it'll change the critical angle, which we'll discuss in a minute. And if it exceeds the critical angle, it's lost in the cladding. It does not come out the other end as a usable component of the signal. We have variations in core shape, maybe somewhat oval, again, bad. And we can have bubbles in the core, and that basically is air. So the numeric index of the core will encounter places of air where the numeric index is 1.0, and that means refraction rather. And we have non-perfect splices. So, and taking this and kind of going down and categorizing it, improper alignment. Now this can be on a connector to lead or photodetector. It can be on splicing two different cables together to make a longer cable. It can be that it's spliced at an angle, that's not good, or it's spliced with a gap in it, and that's not good either, and then all of the above. Now the way these cables are spliced together is that there's a van on a pickup truck, and the cable is pulled out of a manhole and brought into the van and put in an instrument that has a set of mirrors. So what a technician would do on the individual strand after it's been identified by the color and stripped of the protective coating is put the ends of the fiber into this device, and then they look at it, say from the side, and line this up. Of course it would be ideally like this. Line it up correctly. Then they flip the mirrors to look at it 90 degrees to make sure it's not off in that dimension. And when you flip the mirrors back and forth and it looks like this, then they basically melt it together. Then, kind of hard to believe this, they inject light here and measure it here without cutting it. And they can determine the loss of the fuse, of the connection. And if the loss is too high, cut, do it again. So we typically see maybe 0.6 or 0.7 of a dB in a splice, sometimes less than that. Okay, losses continued. This is a good one, micro bending, and it's slightly different contraction rates between the core and the cladding that produces facets. Now a facet would look like this little bump here, and what we're seeing is a blue light ray that's being reflected and another light ray in green which is being refracted. And if this angle is too steep, it's going to be lost on the interface because it's going to exceed what's called a critical angle. And then we have bending period. So here we've got a green ray and it's less than the critical angle, the angle of loss, and because we've bent this too tight, it exceeds that and is lost into the cladding, which I have not shown on the outside of the cable. So typically in a fiber optic bay in a telecommunications operation is they actually have at the bottom of it a set of angles sticking up, posts if you will, that if you have excess fiber you wrap it around these so you don't end up bending it. A kink is the end of the world, and bending produces losses. Now when I worked in the industry, what we were doing, our technicians were doing rather, is repairing fiber optic based equipment. And one of the things we have to be careful of is that on a bench we don't send the transmitter directly into the receiver at a very high level, and we need an attenuator to reduce the level to make it look like a longer piece of cable. So I took a piece of, well, it was a jumper like this, and I was measuring the output while the source was feeding it, and I wound it around a pencil. And every time I would see the output level drop, got to the point where it was in the center of the receiver's allowable range of powers, and then I taped it together. So the way that attenuators really work is if this is the cable, you put it into a device and you tighten a screw which puts a bend in it. Same basic thing. So, and we have another loss called dispersion. And what we'd like to think is that our sources are monochromatic, meaning of one color, but they're not. They have some other components of different frequencies involved in them. And when that goes through the fiber cable, these different frequencies, or wavelengths if you will, suffer different attenuations. So what we get out is that not only attenuation, but different delays. So when we get, what comes out of this is the input pulse only is spread out. And that makes it harder to detect when you have a signal, and further, the spreading can cause this energy to interfere with the energy of the next pulse, intersymbol interference. Now if you think about this from what we learned in FM and AM and sync and so forth, is that if we have a pulse we also have a lot of sidebands with it. And the same is true in fiber optics, except the sidebands are so very near to the main frequency, if you will, that they're insignificant compared to the really, really high frequency. And this is in the terahertz of the actual fiber optic signal, so we can kind of ignore the sideband effects. Further, to increase the amount of payload you can send on a fiber, they have methods of using multiplexed light. and they're basically, a fiber is fed with a couple different lasers operating at different wavelengths. So one fiber can be carrying enough bandwidth, say, for 3 individual fibers, and then at the receive end there are filters that spread out the different colors and go into the correct, I shouldn't say colors, spread out the different wavelengths, and they're fed into the respective detectors so everything gets put back together correctly. So there's a lot of data flying around on fibers, as you can imagine. So if we take a look at this here, we have a cable optic system, and FOT stands for fiber optic transmitter. In this case, it's a light emitting diode, which is coupled into a little pigtail here, and these represent splices or connectors, and it ends up going into a fiber optic receiver. Now the losses we spoke to show up in the loss of the fiber cable, and in this case I've designated 6 dB and 8 dB, and each splice has a loss of 0.7 dB. And our launch power on this is given as a negative 12 dBm. Now remember, dBm is a power. It can be converted into watts. dB is a loss. It's unitless. It would be like, for example, power out divided by power in, where you have watt divided by watt. So what the equation would look like here, and this is called the fiber optic loss, and it'll be called overall the loss budget, is 3 times the number of connector splices we have, plus the loss of one cable, plus the loss of the other cable, so the total loss of the system comes out to be 16.1 dB. Now the word loss means negative gain. So I could say that the gain of the fiber optic system is negative 16.1 dB. That is never used. It's always expressed as a positive number with the word loss in front of it. So the receive level then would be starting out with negative 12 dB, and then subtracting from that the loss of our cable, which is 16.1 dB, gives us a receive level of negative 28.1 dBm, because this is a power. So you have to be careful of dBm versus dB. It's very incorrect to get them confused. Question mark. Is it too high or too low? Don't know. How do we find out? We read the book. This is going into a fiber optic receiver. If it's too low, we've got a bad system design, or maybe one of these cables should be, say, 3 dB, but it's 8. So always have to know what your receiver needs. Have to know what your transmitter's transmitting. If this is wearing out, and they do, because changes happen, these run hot, things tend to move around a little bit. So if the output power drops significantly, it would cause an increased loss of the overall system. It can drop out of range of the receiver, which means, of course, a lot of receiver errors. In laser-based systems, they have a sniffer diode in the laser package, which samples the light. And as that begins to fail, the output of the sniffer diode drops, and it'll actually bring an alarm before the end of life. So there are wear-out phenomena that go on in this. It's just not put it in and it's going to live forever. Okay, so total loss budget, again, another example, only this time we're starting out with a launch power of plus 2.3 dBm. And same basic thought that what we had before. The losses in this case total 16.8 dB, and we start out with our plus 2.3 dBm, add in the losses of the cable, and we end up with a receive level of negative 14.5 dBm, and it's the same question. Is it too high or is it too low? Now, high power fiber optic transmitters have devices in them that if you take and disconnect the cable on the back, it'll turn off the laser. You never, ever want to look into the end of one of these. Bad. It's infrared, you can't see it, you don't know how your lens is focusing it, and you don't want to do any damage to the retina, because it's hard to take an eyeball apart and fix it. Always be careful with this stuff. It's no toy. And the reason, even though this level would be very, very low, if we convert it into watts, is if that's concentrated, the melt steel. Okay, what we're going to do here is take a look at a little video clip, and then we're going to get into the specifics of how the fiber optic cable handles different rays and reflection and refraction and critical angles and so forth. What we're looking at here is the loss characteristics of a fiber optic cable, and the one of interest here is this guy. This is the total loss that incurs a lot of different components. We have OH absorption here, so what we want to do is stay away from, as far as our launch wavelength is concerned, is high places of absorption. So what we can see here is that we have a component of infrared, a component of ultraviolet absorption, and then this huge guy here for the ion absorption. So the typical launch wavelengths are shown down here. One of them is about 850 nanometers, and that would be typically used for multi-mode cable. And then up at 1.3 1310 nanometers and 1550 nanometers, we have launch wavelengths rather, that typically would be used for single mode long distance transmission. So multi-mode is kind of local. The fiber optic cable is cheaper, and you can use light emitting diodes, and on these systems here you have to have lasers. So it's the frequency is the wavelength rather, frequency is the same thing, is chosen such that we're going to try to pick up a minimum loss of the fiber optical cable that would maximize our distance. Next, what's very important is you know that the velocity of propagation in the cladding is greater than that of the core. And that may seem counterintuitive, but it's very important that you keep that in mind. Now, this is a drawing I made of a multi-mode fiber with a lead source launching into a fiber, and is showing different angles, and this is going to be called a cone of acceptance out here in a little minute. If the angle is right, and that means less than the critical angle, the rays indicated in orange will propagate through the cable, and they will be referred to as experiencing TIR, which stands for total internal reflections. If the angle is at the critical angle, the ray of light will travel between the core and the cladding. And remember, the cladding has a higher velocity of propagation than the core, and this ray would be lost to the receiver. If the angle is steeper yet, the refraction puts the ray in the cladding, once again lost as a ray of light to the receiver. Now, for what's coming, we need to be familiar with a planar wave, and this is going to be a light source, and as we can see that the light spreads out from this following the inverse square law. And if we keep going with this, what we can see is a small portion of this will look to be flat. It appears to be without curve, and that's what's referred to as a planar wave. Now, how does light get bent in total internal reflection? And if we take a look at the light ray, is what we can see is the planar wave is coming up through the core, and when it starts to enter the cladding, it speeds up and basically arcs around and gets reflected into the core. And although this is a very simplistic diagram, it gives a pretty good idea of why the cladding core boundary works. And if it wasn't for the fact that the cladding had a higher velocity of operation, this would not be speeding up. And what that basically means now is the N of the cladding is closer to 1, and that's the N of air, than is the core. So the N here is less than that of the core. And a couple equations there. This is a nice demonstration, and it involves taking a piece of acrylic, which is cut in half right here,
And here we have the velocity of propagation is what acrylic is. I don't know what that is, but I know that it is less than the speed of light. And this is a semicircle, and this is referred to, this is the light source, as the ray of incidence, and this is the ray of reflection. So what we can see is it's coming in at a 50-degree angle relative to the normal here, and being reflected at a 50-degree angle. So refraction is bending, and the angles are different, and reflection is where you have this situation right here. The angle of reflection is equal to the angle of incidence. So this is going to be the interface between the acrylic and the air, just like we would have the interface between the core and the cladding. And in this, the velocity is equal to that of the speed of light. This is another diagram which kind of shows in a core and cladding situation, if the angle is steeper than the critical angle, it enters the cladding and is lost. If it's at the critical angle, it travels along the cladding core boundary, and for TIR, the angle 1 here is less than that of the, or actually greater relative to the normal, and the normal is a perpendicular here. It would be greater than the critical angle, and then we would get the reflection inside of the fiber optic cable. So this is another picture of basically the same thing. X here is the critical angle, and they're using air and water here. And water has an N value of about 1.33, where air is 1.0. So the light is going to, velocity of propagation in water is going to be less than that in air. Now we have the cone of acceptance, and this is kind of important because what we have to do is couple light energy into a fiber optic cable to be of any use. So what we're looking at here is anything inside of this circle will be coupled correctly, and once the ray is in the fiber optic cable, it will be subject to total internal reflection. If we're on the actual circle, that would be the critical angle, and light exactly there would be lost in the core cladding interface, and any rays of light entering from outside the cone would be reflected into the cladding and be lost forever. So if we take another look at the cone of acceptance, this is kind of what it looks like, and Snell's law applies here. You just have to be very careful on what your N values are and what your angles are to be able to see this. And this is actually missing this little line here, but it's totally reflected. Another useful drawing is this, and this is showing our air interface A0 and our angles of interest. Now this here has to be greater than a critical angle, and this is the key for solving the angle for the cone of interface. Now remember that the cone is actually this angle times 2, because it's basically a three-dimensional cone, so to speak. So keep that in mind, and this is all based upon Snell's equation. So that's about it for some in-depth diagrams of some of the more difficult components of this course.
So we're going to start out with Snell's law, which is very, very fundamental to understanding fiber. It's the sine of angle 1 divided by angle 2 is equal to the velocity of propagation of one N-type material versus the second type, which is equal to the wavelength, which is inversely equal to the actual numeric index of the fiber. So this is a very flexible law, and it allows us to do a lot. Now let's look at 3 different cases here. And in the first case, we have the core, which is down here. So I'm just showing the core and then the cladding up here. So it's not a complete cable that I've drawn. And in this case, what happens is that our angle 1 here exceeds what's called the critical angle. So it can't be refracted back into the cable. It can't be bent. And because of that, what happens is that it enters and crosses the boundary of the core and cladding and is lost in the cladding, meaning that it's never going to appear at the output in a usable form. So remember, the cladding has a velocity of propagation which is higher than that of the core. So suppose we have a good system for a minute. We kind of really don't have a way of finding out what the angle is, and this is reflection, not refraction, but we can find out really where the critical angle is, and the critical angle is defined, and this here is supposed to be a little bit wider than this in my drawing. It's where it strikes the interface and is bent and travels along the core and cladding boundary. So what that means is angle 2 here is 90 degrees. Now with regard to Snell's law, if we're not given one of these, we can't find the other one because we have one equation with two unknowns. However, in the case of the critical angle, we know that that's 90 degrees, and we can find out then what this is, and then we'll have a reference of whether that angle, if it's less than or greater than, what will happen inside the actual fiber. So let's solve for the critical angle here. And in so doing, this is going to be, I've designated this as the core. And one of the things you have to be very careful of when you work these problems is you define what everything is what your 1s and 2s actually mean, so you can be consistent. So this is the core, this is the cladding, and it's equal to N2 over N1. And since I know that the angle number 2, which is this guy, is 90 degrees, I can just take the sine of 90 degrees in Snell's equation, and taking the two numeric indexes and dividing those out, all I have is one variable here, which is going to be the angle. It's called a critical angle. And then working this out, I have the sine of the angle divided by 1, because the sine of 90 degrees is 1, and that equals, the ratio of these two are 0.960. So the angle is going to be equal to the inverse sine of that, and in degrees that comes out to be 72.9 degrees. So this is not to scale here, so this angle would really be considerably larger. But okay, so that's the way you know the critical angle. Now when you know the critical angle, anything less than that is going to cause the ray to disappear into the cladding, and anything greater than that, be the angle over here, the cable would feature total internal reflection, which is what we want. So at least we know what the boundary is for a given cable. Now this is going to be useful coming up because we've got to couple energy into the core of the cable. So let's talk about that for a minute, and this is going to be our source, and this guy is called a normal. And a normal, matter of fact, let me go back for a second here. This is a normal, and this is a normal, and this is a normal, and it's just an imaginary line which is 90 degrees relative to the interface. So this will be the normal of the center of the axis, and if I were to draw it as such, I could put another normal right down here where this strikes the interface. Now here's the problem. We're launching this from, say, a lead, and we have many different rays, and what we want to do is make sure that those rays meet the total internal reflection criteria of the angle for inside of the cable. So this is going to lead us into what's called a cone of acceptance. How do we find out what this is? Now there's a bend right here. I have not shown it because we're going across the boundary from a high speed velocity, that of speed of light, into a lower velocity of propagation, which is the actual core. So this is called the numeric aperture NA, and it's a figure of merit, and it's going to be a number which we can break down to figure out what this is. And what we're going to end up doing is taking this and rotating it and making a cone. And anything within that cone is going to be accepted, anything on the cone, the actual edge of it, will end up in the core and cladding, and anything outside of the cone will end up in the cladding. The latter two cases are not useful. So numeric aperture is a figure of merit. How good can the cable accept a signal coming in and couple more light into the actual core? And it's defined as the square root of the N core squared minus the cladding squared. Remember that the core is going to be a larger number. Now there's another term sitting out here I didn't show, which is equal basically to 1. It's 1 over NA, that's the N of air, which is 1.00 something something 6. So we're calling it 1, didn't put it there. And if we work this out for the given examples of the N values that I made up, this comes out to be 0.369. So taking the inverse tangent of that gives us 21.65 degrees, which would be this guy in here, between this here and here. So our angle for the cone of acceptance would have to be light rays that are less than that get effectively coupled into the fiber. Now we have another loss. It's called reflectivity, and I've specified that N air here is equal to 1.0. And that since we're dealing with basically, if you will, glass similar, there's going to be reflections. And reflections mean that part of the energy of the light ray is not going to be coupled into the cable, and you can kind of see that here. We have a ray which is within the cone of acceptance. It should be good, and yet part of it's going to be lost because of reflections within the cone of acceptance, so it should be good. Okay, so reflectivity is defined as the N value of the core minus N air divided by N of the core plus N air, and if we work out the math on this, as we end up with a value of 0.18, and converting that into a percent would be 1.8% reflection. So reflections are bad. They subtract from the overall power. And everything in a system is about getting the launch power into the receivers, photodiode, avalanche diode, whatever. So this will be followed by a small video clip on a little bit of the electronics, and thank you for watching. Let's talk about some of the electronics and related that supports the operation of fiber optic transmission. And what we're looking at here is a very simple fiber optic receiver. And what we see is we have a photodiode here, and the arrows pointing into it mean that it's a photodiode, or we could have the lambda symbol here also. So this is basically a current to voltage converter, and the direction of the current arrow should not be of concern. Since the non-inverting input is at 0 volts by way of a virtual short between these two terminals brought about by the operation of the operational amplifier, is this basically is working very, very near ground. So this current is being generated totally by photocurrent and function of saturation current. The current then flows through RF, and we see the output at the ground, which, I'm sorry, V out, which would be a relatively low impedance source. And then if we needed to, we could amp it up and convert it into a digital voltage or whatever that we need to satisfy our end purposes. Now this here is a comparison of different receiving materials, and what we are comparing this to is the human eye, which is this guy right here. This is human vision. And we have the sensitivities of selenium, which is not going to work well, silicon, which is okay because its peak is right here, which is where we operate infrared in the 800 nanometer. And then we have germanium, which does an excellent job up here in the 13 to 1500 nanometer area. Now, one of the things to be careful of is when you look at this is the units for this is in angstroms, angstrom units, and fiber optics talk about nanometers. So it's very easy to convert. All you do is move the decimal point one place to the left.
So at 7,000 angstroms here, that would be 700 nanometers, which would represent red. So silicon has its advantages for near infrared, and that's typically used in multi-mode cable. And then germanium has its advantages out here, where we're dealing with single mode emitters. Now, these are usually LEDs, and these are lasers. So how does a photodiode work? And to start with, it has to be made out of glass. That's kind of a good place to begin. This is a typical diode, and it can generate a photocurrent, but an improvement it is made is if we insert an intrinsic area between the P and the N, hence the word PIN, P-type, intrinsic, N-type. And what this does is it increases the ability, and here's our depletion zone here, notice how large it is over here, of generating photocurrent. So if a photon strikes an electron hole pair and generates an electron hole pair in the depletion zone, that turns into external current. So it's a whole lot more sensitive than a standard glass diode for generating a photocurrent. Now we have an interesting variation in theme, and that's the avalanche photodiode. And this are its benefits here. It has better sensitivity, it's noisier, and it requires more complex circuitry. Now before we actually look at the diode, let's take a look at the circuitry here. And then what we see is we have an amplifier, and this is the photodiode, and we have the little lambda symbol there that indicates it's associated with light, and it's reverse biased by a variable supply. And that reverse bias brings it very close to its breakdown voltage, and if you remember that when a diode breaks down, very small changes in breakdown voltage lead to very, very large increases in current. So if we take a look at this now with that in mind, what would happen in words is that if an electron hole pair were to be generated, the electron would go speeding toward the positive terminal, and in the process would be passing other electrons and conveying a little bit of energy to them. So they could break free and enter the conduction band, and they in turn would influence other electrons, which would generate other electron hole pairs. So one photon can generate anywhere from 80 to 100 electrons. So we get this multiplication effect. Now that may sound nice, but the problem is that when you say 80 to 100, if it's not consistent per photon, it can end up being treated as noise. So an APD is a little bit more noisy than a standard PIN diode, but it's a whole lot more sensitive, and sometimes very much worth the added expense of putting this in. Now this is a little bit more involved than a variable power supply and a resistor, as you can probably imagine, to make sure that this operates at the correct place. So that's called an APD, avalanche photodiode. Operates on the very edge of breakdown. Now if we take a look at a regular PIN diode, what we see is if it's not illuminated, we have a dark current here. And that is the saturation current. It's caused by impurities and also by thermal agitation, because it's above 0 degrees Kelvin. And we can see here it's relatively low. It's sitting here maybe, I'd guess, about 25 microamperes. And then if we expose it to light, say 1,000 foot candles, we see a whole large increase in the current flow. Now remember, this is the reverse voltage. And as we continue to add light to it, or increase the intensity of the light, is that more and more current flows. And it's relatively linear. And note that it tends to look like a current source, meaning that the slope is relatively close to zero. So that's what we would expect a PIN diode to do with regard to illumination. And then what we can do is take whatever illumination we have and see what we would need to do with regard to the first circuit we saw to get that into a level which would be able to be amplified and further conditioned. Now, when we talk about emitters, that's kind of a different topic. This is a standard diode here which is not forward biased, and we have two levels here. One is the valence band and the other is the conduction band. And it takes energy to move an outer valence electron into the conduction band where it can be moved very, very easily. And this is the distance in energy, E stands for energy, that has to be added to get the electron to enter the conduction level. Now when we apply bias to that, the difference is much less. So we can have electrons enter the conduction band, and when they return, what they do is generate an a photon here is generated by H. So on the recombination of an electron and a hole, it produces a photon. So it doesn't stay in the conduction band very long before it returns, and the distance between the valence band and the conduction band here determine how much energy the photon has. That is, its color. So if it's a blue photon, it would have higher energy than, say, an infrared photon. Now, to get these different energy levels, additional dopants are put in the junction here. Very strange metals. I don't remember the names of them, nor do I need to. But as the band gap increases, so does the photon energy. Now this is a diagram of a light-emitting diode designed for fiber optics. It's very general. We have an N-type substrate which serves as the foundation, and we have a thin P layer on top. And what occurs is that we have the generation of electron-hole pairs that release photons, and notice that the photons go in all kinds of different directions. So unlike a laser, it has to be focused by some external means, and there have been advances in diodes that do that. Now the reason that the P-type layer is so thin is the photons are actually generated at the junction when electrons are forced across the junction by the forward bias, and when they recombine is when a photon is emitted. Now a very special type of diode is designed such that the fiber pigtail can be plugged into it, and the light that's emitted can very easily enter the pigtail, and that makes it highly efficient for coupling. Now if we have a laser diode and we start to apply current to it, bias current here, and we compare that to optical power output, so we see it has two modes. Over on the left here, where the current is relatively low, it operates in the LED mode. And in the LED mode, like all LEDs, is the output light is proportional to the current, as long as it doesn't overheat. And then we reach a point where there's a population inversion. And what that means is that the photons going back and forth in this, as we'll see, they oscillate from end to end, actually generate other photons. It's like an avalanche effect again, which then causes this to enter into the laser region here, and there's a tremendously large increase in output power for the bias current that flows through it. Now notice that the power is a function of the bias current, not the voltage. So this is an injection laser diode, and we would have to be operating above the point of the population inversion. So here we actually see a laser diode, N-type, P-type, and there can be other materials in between here, the junction, that help set the band gap to what we want. And in the back we have a completely reflective surface. In the front, a partially reflective surface. So what occurs is, as we generate electron hole pairs that decay into photons, is that the photons go back and forth and so forth, cause other photons to be emitted, and this is above the population inversion point. And population inversion simply means that more of the atoms near the junction are excited than not excited, and we get this wave going back and forth, and part of it can then escape from this partially reflective front surface. So when this is in fact in the laser mode, is we get relatively high power output, and notice that this is not a spot. It comes out parallel. So diodes, if we could look at this, we would see kind of like an oval pattern, and then that has to go into a micro lens which focuses this, and since laser diodes are typically used with single mode cable whose core is quite small compared to multi-mode, is it has to be focused very precisely so that it can pick up the core itself without any losses in the cladding and things like that. So that's the core of electronics that sits under the hood that makes fiber optic communications feasible.